Hello and welcome to our next lecture in CHY 113. This will be our second lecture on chemical equations and chemical reactions. Last time in our first lecture on this topic, we focused in on the basics of chemical equations. We looked a lot at how we write them, what the parts of a chemical equation are, and then we talked a lot about how to balance a chemical equation in order to satisfy the law of conservation of matter. We ended last time by starting to look at some particular types of chemical reactions. In particular, we looked at precipitation reactions and using the solubility rules. And if you remember, the reason why those are important and what they're used for is to start looking at some of these driving forces of a reaction. And one of the things that drives a reaction, one of the things that can cause a reaction to happen is the formation of a precipitate. And so we have to use our solubility rules to determine if a precipitate forms or not as one of the products of our reaction. And so today we're going to look at some more detail on those and look at how some of the ways that we depict precipitation reactions. We'll look at some acid-base reactions and some definitions there. Then we'll look at a couple other driving forces, such as the formation of a weak electrolyte, which is what drives an acid-base reaction, and some gas-forming reactions. And finally, we'll close out today by looking at what we call redox reactions, oxidation reduction reactions. And so we talked about these last time. We talked about using our solubility rules, that we have to use our solubility rules to predict if a precipitate will form or not. And so remember, we had two basic categories. We had our list of soluble compounds, and with some notable exceptions on here. And remember that any of these exceptions mean that compound will not be soluble. So for instance, NaCl is soluble, but AgCl is not, and so on. LiF is soluble, but CaF2 is not soluble. And that's the way that we would use our solubility chart. And then we have our insoluble compounds. So most of the compounds that appear, or most of the compounds that have ions that are on this chart are not soluble, with some notable exceptions. And I remember that I will give you access to this solubility chart, or I will allow you access to these solubility charts on the next exam, so you don't have to memorize these rules. A precipitation reaction will happen by way of what we call an exchange reaction. In an exchange reaction, we mentioned this a little bit last time when we looked at a precipitation equation, but in an exchange reaction, you can view it as the anions exchanging with each other. And so here we have just generic equations, AX and BY. What's going to happen is that Y is going to now come together with A to form one of our products, and X is now going to come together with B to form our other product. Now, it's important to also keep in mind when this happens that your new equations, your new formulas, AY and BX, will be governed by, or those formulas will be governed by the rules of writing chemical formulas. And so you have to look at the ionic charges to determine what the new formula is going to be. Just because you have a certain subscript over here in the reactants, say this was whatever equation this happened to be, say this happened to be X2, you're not necessarily going to have a 2 on this X, just because of the way B and X are going to come together. So we have to keep that in mind, and that ultimately is why we end up needing to balance our reactions. But let's say one of our products, either AY or BX, we consult our solubility chart, and we find that one of these products is insoluble. That's what we mean by a precipitate forming. Now, when we talk about an insoluble precipitate, we talk about an insoluble solid forming from one of these reactions. It's not so dramatic as in, like, I take two liquids and I pour them together, and then clink, a pebble falls to the bottom of the test tube. It's nothing as dramatic as that. Quite often what it means is you'll mix a couple maybe clear liquids together, and you'll see this white cloudiness start to appear. You let it sit for a while, some little white flakes then start to appear up top. Sometimes it is a dramatic color change. We'll see a couple of different examples of that, of something that the new compound that forms is brightly colored compared to what was there. But the bottom line is that something for a solid is formed which does not stay dissolved in water. And so that comes out as a precipitate. That will come out as a solid. And we can see, actually an example here. What's pictured, I believe, if I remember right, is actually this equation here. We have lead nitrate plus potassium iodide. Now our products from that reaction are going to be potassium nitrate and lead iodide. We consult our solubility chart and we see that potassium nitrate is soluble. That's going to remain aqueous. Lead iodide, however, is not solid. Remember that most iodides are soluble. Lead, however, is one of the exceptions. Lead iodide is an exception to that rule. So it's not soluble, so that comes out as a solid. And that, like I said, I'm pretty sure that's what we see actually pictured here, is the formation of that lead iodide. And then another example, barium chloride plus sodium sulfate, aqueous solutions mixed together. We consult our solubility rules, and one of our products, barium sulfate, is not soluble. So that will come out as a precipitate, whereas sodium chloride is soluble. Now again, remember, like I said, our products and the formulas are determined by the rules for coming up with a chemical formula. We see that happening here. Sorry about that. So for instance, there's no subscript on the I over here on our reactant side because Ki, potassium iodide, +1 and a -1, we have a formula of Ki. However, we do have a 2 for our iodide in lead iodide because our charge on lead is a +2. And so this needs, the formula for lead iodide must be PbI2. And that ultimately is what will lead to our 2 here for our balancing. So keep that in mind as you're writing chemical formula or chemical equations. And here's just a few different examples of some precipitates forming. We have some lead chromate, which forms from the combination of lead nitrate and potassium chromate. Some lead sulfide, if we mix together lead nitrate and ammonium sulfide. Some iron 3 hydroxide, mix together some iron 3 chloride and sodium hydroxide. And then some silver chromate from silver nitrate and potassium chromate. And so if you mix these together, you see this solid start to form, and the solid is a different color, and we can actually visualize that and see it in these examples. So a few things that we have to define, a few terms we have to define so that we can go on and see how we depict and how we write the chemical equations for precipitation reactions. We have what we first call the molecular equation, or the complete equation. This is an equation which is written as if all substances were molecular, even though some of them do actually exist as ions. This is what we are used to seeing for a chemical equation. The equations here, for instance, these would be considered molecular equations. We know that lead nitrate and potassium iodide, we know that those are ionic. They're ionic salts. But we write them as if they're all together and as if they are molecular and just all bound together still. Even though we'll talk about what happens as aqueous, that they actually do dissociate in water. But in a molecular equation, we write it as if they are all still together. We also have what we call an ionic equation. Here's where we're going to take any ionic substances and now actually split them apart into their constituent ions, which actually is a depiction for how things actually exist when they are in aqueous solutions. And we'll see what that means in just a minute. And then we also have what we call spectator ions. A spectator ion is an ion that doesn't actually take part in the reaction. It's something that is present in aqueous form in the reactants, and it's still present in aqueous form in the products. It doesn't actually, it's not one of the ions that comes together to form the new precipitate. We'll take a look at how we deal with those. A net ionic equation, now we've removed the spectator ions from the equation. We've removed anything that is not actually participating in the precipitation reaction. So here's an example. So we just saw the molecular equation for our lead nitrate plus potassium iodide, and it forms our potassium nitrate and our lead iodide. And remember, the way that we would come up with this is by looking at what our charges are on all of our reactants. then looking at our new combinations and what our formulas have to be for those combinations. And then after we come up with our chemical formulas for our products, we're then going to balance the reaction. That's where these 2's come from. And then lastly, we would use our solubility rules to determine what phase each of the products are going to be in. When we do that, we see that potassium nitrate is aqueous, that's going to remain dissolved, whereas lead iodide is going to come out as a precipitate. Lead iodide is going to be a solid. And so that's then our molecular equation for this particular reaction. What we're going to do next is we're going to split up anything that is aqueous into its actual ions and depict it that way. And that's what we see here. So our PbNO3, our lead nitrate, actually an aqueous solution. Remember, those are going to dissociate. That's what ionic substances are going to do in water. They'll dissociate into their ions. And so what actually exists in this aqueous solution, for every 1 unit of PbNO3, we have 1 Pb2 plus and 2 NO3 minus ions. Likewise, for our potassium iodide, we have 2 K pluses and 2 I minuses, and those are all aqueous. In our product side, our KNO3, our potassium nitrate, is aqueous. So we'll have 2 K plus and 2 NO3 minus coming from our KNO3. Our lead iodide, our PbI2, that's a solid. And so we still depict it that way because those actually are locked together still. The lead and the iodide are locked together in their ionic lattice. And so that's how we depict it in the total ionic equation. We depict it as actually together because that's how it really exists. What we can do now, or sorry, we never break up any solids, liquids, gases, or anything that's molecular in our total ionic equation. And that'll be important for us later on. And what we can start to do now is to look at our spectator ions. We want to take a look for any ions that are in aqueous form in our reactant side and remain in their aqueous form in our product side. And so we can see, for instance, that our NO3 minus and our K plus, our potassium and our nitrate, are both aqueous as reactants, and they're also both aqueous as products. This means that they're not really participating in the reaction, so to speak. The only things that are really participating, the only things that are really taking part in making something new are the lead and the iodide. And so we're just going to cross those right out. We're going to cross out our potassium and our nitrates because those are, again, are not actually participating in the formation of the precipitate. Once we cross those out, what we're left with is our Pb2 plus our 2I minus forms PbI2. That is our net ionic equation. That depicts the actual chemical reaction that's taking place. It shows us the only real change that is occurring throughout this process. The nitrate and the potassium, they're there because they had to be used really in order to bring the lead and the iodine along. And so as these sit on the shelf, before we even get these into aqueous form, we would probably have in a chemical stock room somewhere, we would have some lead nitrate, some PbNO3, sitting on the shelf in a solid form. And that's one of the ways that it would exist, is just in its solid form, so sitting there in either like a crystalline or a powdered form, and it exists as a solid. Likewise, also the Ki is going to exist as a solid. And so then once we dissolve it, though, that's when they split up into their ions. And so really one of the ways that you can sort of view this is that the only job of the nitrate is to give lead a ride to the party. That's what it's really doing. As they exist as solids, they're bound together. And so the nitrate is pulling the lead along into the reaction and into the water. But then once it gets into the water, they're going to split apart so that lead can go on to participate in the reaction, but the nitrate's just going to sit around still. Likewise, the same with the potassium iodide. in their solid form, they are existing as Ki, both of them locked together. But then once they get into water, they're going to split apart. So all the potassium did was it just gave iodine a ride to the party. One of the analogies that I use sometimes that's kind of foolish, but it works because it sticks into your heads a little bit, I think. Picture spectator ions as a creepy Uber driver who sticks around at the party. You know, they brought you to the party. Now they're just sticking around and checking everything out. Same exact thing here. Nitrate brought lead along to the party. Potassium brought the iodide ion along to the party. And then the potassium and the nitrate, they stuck around. They didn't do anything. They were just spectating. They were just watching. They didn't participate in the reaction, but they were still there. Those are our spectator ions. Let's look at some other examples. So we're going to write precipitation reactions. We're going to write net ionic equations for these three different reactions here. So sodium hydroxide plus copper 2 nitrate, silver nitrate plus barium chloride, and ammonium sulfate plus magnesium iodide. So it'll be helpful if we leave our solubility rules up. So let's leave these up as we look at these examples. Shrink it, we'll just shrink them down a little bit so we can use our whiteboard. Okay, so our first example so we have NaOH, and these are all in aqueous solutions. So NaOH, aqueous, plus aqueous copper nitrate. And so our first step is to figure out our products. And so we're going to go through our process of looking at our charges, +1 for sodium, a -1 for hydroxide, +2 for copper, and a -1 for nitrate. That now gives us the information we need in order to find our new products. So we're going to go for our new cation anion combinations, our new plus-minus combinations. And so the first one that we might write down is NaNO3, +1 and a -1 coming together. We also have CuOH2, +2 and a -1 coming together. So there's our first step along the way. Now we still need to balance this. And we can see to balance it, I'm going to need to put a 2 here and a 2 here. Make sure that you understand why all the subscripts and coefficients are the way that they are. Also take note of the fact that OH, the hydroxide, and NO3, our nitrate, those stayed together because those are polyatomic ions. One of the reasons, like I mentioned in the last unit, why it's so important to have those memorized so that you can see what is going to stay together. And so now we have our equations, we have it balanced. Now we're going to use our solubility rules. We can see that, again, almost all salts of sodium and salts of nitrate are soluble. Tells us that our sodium nitrate is going to remain aqueous. Our copper hydroxide, on the other hand, most metal hydroxides are insoluble. There are some exceptions, but copper is not on that list. So copper hydroxide is insoluble. So it's going to be a solid. So there's our complete molecular equation. Now we want to write out the ionic equation. Anything that's aqueous, we're going to split up into its constituent ions. Blow this back up a little bit. We'll bring the solubility rules back when we need them. And so first we have our NaOH. So we have 2 Na plus and 2 OH minuses. We have a Cu2 plus, 2 NO3 minuses. In our product side, 2 Na pluses, 2 NO3 minuses, both aqueous. I thought I could fit it all on one line, but I can't. And then our solid, our CuOH2 solid, our copper 2 hydroxide. And so there's our complete ionic equation now. And so then our final step in getting to our net ionic equation is we are going to cancel out any ions that are aqueous on both sides of our equation. We can see that we have 2Na plus and 2Na plus, 2NO3 minus, 2NO3 minus. The only things that remain, and typically we write in the order of our positive ion first, but either way. But so what we have remaining is Cu2 plus aqueous plus 2 OH minus aqueous forms Cu OH2 solid. And there's our net ionic equation for this reaction. So let's go ahead and look at our next example now. So our next example was silver nitrate reacting with some barium chloride. So again, we're going to go through and look at what all of our charges are. Charge on silver is a +1, nitrate's a -1, barium's a +2, chloride is a -1. And so one of our plus-minus combinations is +1 silver with -1 chloride. Our other positive-negative combination, +2 barium with our -1 nitrate, so we get BaNO3 2. So we've determined our products. Our next step is to balance. We're going to need 2 chlorides on our product side. That now gives us 2 silvers, so we need to place a 2 here, which gives us 2 NO3s, which works out because we have 2 NO3s in our product side. And so we now know what our products are. Let's use our solubility rules to determine their states. So we look through, we have silver chloride. We do have a rule here concerning chlorides. Almost all salts of chlorides are soluble. However, silver is an exception to that. So silver chloride is not soluble. So that will be a solid. Can't manage to write an S in parentheses right now. There we go. Nitrates are soluble, and there are really no exceptions to that. And so barium nitrate is going to be soluble, so that's going to remain aqueous. And so there's our complete molecular equation for this reaction, sorry. And so now let's break that up into our ionic equation. So we're going to split up our silver nitrate, 2Ag plus, plus 2NO3 minus, so our Ba2 plus, 2Cl minus, forms our AgCl solid, plus our Ba2 plus and our 2NO3 minus. So now we have our complete ionic equation for this reaction. Our next step is to determine our spectator ions, and we can cross those right out. We see that we have 2NO3 aqueous reactants and 2NO3 aqueous products. We have a Ba2 plus aqueous reactant, Ba2 plus aqueous product. So those can disappear. And so finally what we have left, 2Ag plus aqueous plus 2Cl minus aqueous gives us 2AgCl solid. And then we just want to reduce that down. So we get our final net ionic equation. One more final example. We have a reaction of ammonium sulfate plus magnesium iodide. So again, we go through our process, +1 for ammonium, -2 for sulfate, +2 magnesium, -1 for iodide. So one of our combinations is going to be ammonium iodide, NH4I. Another combination, magnesium sulfate, MgSO4. And then we finally need to balance, and we can do that by just putting a 2 right in front here. And so now we want to look and see if our products are soluble or not. And so we have ammonium iodide. So we have a couple rules we can look at. Everything pretty much made out of ammonium is soluble. Most salts of iodide are soluble, and ammonium's certainly not an exception there. So ammonium iodide is going to remain aqueous. Sulfates, we see, are on our soluble list. There are a number of exceptions, but magnesium is not one of those exceptions. And so that would remain aqueous. And so what we see here is that really nothing new forms. All of these ions are remaining aqueous in solution. Let's even look at the breakdown of the ionic equation for this one. We have 2NH4 plus AQ, SO4 minus AQ. We have our magnesium. So there's all of our reactants. And then our products. And so we can see that nothing changes. We have 2 NH4s, an SO4, an Mg, and 2 iodides on our reactant side. We have 2 NH4, 1 SO4, 1 Mg, and 2 iodides on our product side. Nothing at all changes. Everything is remaining aqueous. All that we're doing is we're dumping 2 solutions together, and all these ions are just swimming around in the solution there. Nothing new is being formed. And so to depict this, where really no reaction happens, that's all we write down. And so to write we even have a net ionic equation for this. We would write this literally as just showing no reaction. Just like that. Sometimes we might abbreviate reaction as RXN. But that's it. That's how we would write this, because no actual reaction occurs. There's no precipitation reaction that goes on. And so we write that down like that. There's no reaction because everything remains in its aqueous form. Let's look at this example here. Here's another example of a couple of different ions. Or a couple different ions that are going to come together in a chemical reaction. So we have HNO3 plus KOH. So they're going to come together, and if we look at our charges, we have H1 plus, NO3 1 minus, 1 plus for our K, -1 for hydroxide. So one of our combinations is going to be our potassium. Sorry, I'll keep the colors consistent. Here we go. Potassium coming together with nitrate. We consult our solubility rules. We see that nitrate is aqueous. Our other combination is HOH. All right, that's our other plus-minus combination here. What's another way that I can write HOH? Just H2O, right? Now, H2O is not aqueous. Water's not dissolved in water. This is going to be in its pure form, and we're assuming room temperature and normal conditions, all that. And so water is now going to be a liquid. And I sometimes try to use the cursive lowercase l, just so that it's clear it's an L. And so that's going to form H2O liquid. Let's keep this in mind, because where this is bringing us, and maybe you recognize these, HNO3 That's an acid, right? That's nitric acid. We looked at that and we saw that during our naming rules when we were talking about molecular compounds. KOH, that OH makes it a base. So this is an acid-base reaction, which leads us into our next topic quite nicely, looking at different aspects of acids and bases. We're not going to get into a lot of detail in this class on acids and bases. Those of you that do go on to 115, you will talk about acids and bases a lot. It's going to make up a pretty major portion of your semester. For now, we're going to look at some basic definitions and some general acid-base reactions. One of our definitions is what we call the Arrhenius definition of acids and bases, which states that an acid is just any substance that increases the H+ concentration. And so remember when we looked at that with our naming of acids, and we talked about hydrogen being basically if you see hydrogen in the front, pretty sure that's an acid. And so then when that dissociates, when that splits apart, we're going to have H+ in the solution. And so that's the definition of an Arrhenius acid, is anything that increases that H+. Whereas the definition of an Arrhenius base is anything that increases our OH-. And so M, just kind of standing for a generic metal there, that's not a specific element, it's just generic, is going to split apart and it's going to dissociate. And as it does so, that hydroxide, that OH-, is going to split apart and split off now. And so an Arrhenius base is any substance that increases that amount of OH-. Now, it was found that there were some substances that kind of behaved as bases and had similar properties to bases, but didn't necessarily have OH-. And so we came up with, or not me personally, but in general, the collective we, came up with another definition of acids known as the Bronsted-Lowry definition, where now we're going to say that an acid is anything that donates an H+ to another species. And so in other words, we have our general acid HX added to water that generates what we call what is H3O+. And so this H is just getting added to the water. You see that here, but that changes our charge. So we have H3O+. And then the X is now dissociated into X-. This is called the hydronium ion. And so just take note that really in an acid, the hydronium ion is what really exists. So we talked about acids in the case of Arrhenius as being H+. This is really what's going on, is that once that H+ hits water, it'll form H3O+, it'll form this hydronium ion. You might see it written either way. And so I just want to point that out because really we're talking about the same thing. You might see H+ written, you might see H3O+. It's really the same thing. And so it's important to take note of that. But then our Bronsted-Lowry definition of a base is it's anything that will accept H+. So here's sort of our classic example of a Bronsted-Lowry base is ammonia, NH3. Definitely is a base. It behaves like other bases. But you can see there's no OH- in there. And so, it's just a different way of looking at things rather. And so when H+ is added to ammonia, it forms our ammonium polyatomic ion. And we can see that in doing so, in going from our reactants to our products, NH3 is accepting this H+. Makes it a Bronsted-Lowry base. Now, just another sort of, terminology note. Think about this question for a minute. If we have this particular species, if we have hydrogen 1, and it's a 1+ charge, think about this question for just a second. How many protons, neutrons, and electrons are existing in this species, in hydrogen 1, 1+? Come up with it? 1 proton, no neutrons, and 0 electrons, right? Hydrogen 1, that's our mass number is 1. That's our combination of our protons plus our neutrons. So if it's hydrogen 1, got to be just 1 proton because the atomic number of hydrogen is 1. So there can't be any neutrons in there. 1+, so a neutral hydrogen atom will have 1 proton and 1 electron, but this is a positive 1 charge. So it had to have lost that 1 electron. So that species, that H plus, is really just a proton. That's all it is. It's just one naked little proton floating around. And so that's another thing to note is that the terms H plus and proton are quite often used interchangeably. And so we'll sometimes talk about the Bronsted-Lowry, instead of saying H plus, we'll say donates a proton, or a Bronsted-Lowry base accepts a proton. Same thing. A proton is just an H plus. So keep that in mind as we move forward as well. And so just as a recap, acids are any species that increase the amount of protons, increase the amount of H plus. They'll ionize in aqueous solutions to form some H plus. Remember that H plus is just a proton. So we call acids proton donors. Bases are anything that will increase the amount of OH minus. They might ionize, or they do ionize in aqueous solution to form OH minus, and bases are often called proton acceptors. Now we need to look at what a strong acid is. You've probably heard that term a couple times by now. Strong acid versus weak acid. A strong acid is any acid that will completely dissociate into its ions. And so every bit of it that ends up into solution is going to break apart into its ion form. And so, for example, sorry, my slides aren't quite coming through here the way they should. But HCl, hydrochloric acid, is one of our strong acids. And so every bit of it is going to break apart and no longer exist as HCl bound together. The hydrogen is going to dissociate, react with water to form our hydronium ion, and then the Cl minus as well. So every bit of that HCl, all of it completely splits apart. Whereas a weak acid does not completely ionize. Most of it actually remains in its molecular form. So here's acetic acid, which is a weak acid. Only some of this, only a little bit of this acetic acid is actually going to dissociate to form our hydronium ion and the acetate ion. Most of it's going to remain together like this in its molecular form. So that's what a weak acid is. It's something that will not completely dissociate. And that's why we see these different types of arrows here. A full, sort of a forward reaction arrow to show that this is all going to bust apart, versus an equilibrium arrow to show that all of these are going to exist simultaneously. It's another big part of what 115 will be about for those of you that go on, is looking at the details behind this equilibrium and seeing how many or how much of what might exist in an equilibrium. And so strong acids completely dissociate in water. Weak acids will only partially dissociate in water. Most acids are weak. We'll see how to tell the difference in a second. Strong bases also completely dissociate in water. And weak bases only partially dissociate in water. And so a weak acid, any acid that's not strong, is a weak acid. So it's important to note that. And since weak acids ionize to just such a small extent, really it's mostly the molecular species which will predominate. And this should have a little arrow there. I'm not sure where that went to. Sorry about that. So let's see if I can bring that back. Let me pause you here real quick. Sorry about that, but that would have bugged me. There we go. There's our arrow back. And so weak acids ionize, they dissociate to such a small extent that mostly what exists is this molecular format. And so, for example, in a solution of acetic acid that has pH that has a concentration of 0.1 molar, that should not say pH. I'm going to go ahead and pause you and fix that right now too. Okay, so for example, a solution of acetic acid that's at a concentration of 0.1 molar, only about 1 1/3% of that is actually going to dissociate. And so only 1.33% will end up splitting up into the H3O plus and acetate ion. The rest of that 98.67% is going to remain here in the molecular form. And so that's important to know about weak acids, is that's what's really going on. It's not all splitting up like strong acids do. So hopefully what you're asking yourself is, okay, well, a weak acid is anything that isn't strong. How do I know what the strong acids are, Professor Staples? That was less dramatic because it should have just gone on. There it is. You memorize this chart. That's sort of the bottom line. Now, you don't have to memorize the weak because, like I said, any acid that is not strong is weak, so you don't have to memorize these, but you do have to know your strong acids. And so HCl, HBr, HI, HNO3, HClO4, and H2SO4 are all strong acids. Memorize them. If you have an acid and it's not on that list, it's a weak acid. Likewise, the strong bases, lithium hydroxide, sodium hydroxide, potassium hydroxide, barium hydroxide, and strontium hydroxide. All strong bases. Any other base is weak. And so as long as you memorize these, then you'll be all set. Now, one other thing to take a look at with the behavior of acids and bases is what we call polyprotic acids. And so in a polyprotic acid, there's more than one H plus that can split off. And so, for example, if we look at HCl, so HCl can split up into H plus and Cl minus, and that's it. That's all it can do. Sulfuric acid, H2SO4, can split up into H plus and HSO4 minus, but look what's still available. On this HSO4 minus, we still have another hydrogen that could dissociate and split off. And so that can then split into H plus and SO4 2 minus. Phosphoric acid, H3PO4, can split up into H plus and H2PO4 2 minus. That can then split and dissociate again into H plus, HPO4, sorry, I'll have to go all the way back. Hopefully somebody corrected me in their head and said, Professor Staples, that should be a 1 minus, and you're right. And that H2PO4 1 minus can then dissociate into H plus and HPO4 2 minus, which can then split once again into H plus and PO4 3 minus. And so the H2SO4 and H3PO4, anything with more than one hydrogen that can split off, more than one hydrogen that can dissociate, is what we call a polyprotic acid. Now, let's go back to an actual equation for acids and bases. When a strong acid mixes with a strong base, we call that a neutralization reaction. The net ionic equation will always be this. Always, always, always. That's the same net ionic equation that we looked at a couple minutes ago. So it's our equation that we saw right here. So let's take a look at that equation and write it out as a net ionic equation. Okay, so let's write the net ionic equation for this. Let's just erase our words here below. Okay. And so we have our HNO3 and our KOH. And our KNO3, which is also aqueous. Then our H2O, which stays together. So then we go through and we cross out our spectator ions, our NO3 and our K, remain the same on either side. What we're left with is H plus OH minus gives us H2O. That's our net ionic equation for this neutralization reaction. Now again, note the difference here. The only difference in this equation is we're working with a hydronium ion, so we form two waters. Really no different. It's just a question of if we are going to depict our H plus as H plus or H3O plus. Same thing either way. But our net ionic equation will always be in that form for a strong acid and a strong base. And here's just the same thing working through the example, but just with HBr and KOH. And we can see again, we come up with our ionic equation here. Cross out our spectator ions, and we end up with our net ionic equation. Oh, so back up. So the general form of a neutralization reaction, your acid plus your base will, sorry, what's going on here? Here we go. Are going to react to form a salt plus usually a water. And so the salt in this case being our ionic salt KBr, which typically are always going to be aqueous. And so the driving force, let's back this all the way up to when we started talking about driving forces earlier on. The driving force of an acid-base reaction is that formation of water, which is a weak electrolyte. We haven't talked about that, but water is a weak electrolyte because water will split up into H plus and OH minus. And so it will partially dissociate. It just doesn't do it to a large extent. Only a very little bit of it does. And so for our purposes, for a class like this, we don't really consider that dissociation important for what we're going to do. Again, those either go to 115, you are going to look at this dissociation and look at some details on that. For our purposes, we just need to know sort of that it does happen, which does make water a weak electrolyte, which means that it is the driving force behind an acid-base neutralization reaction. Now, let's say we have a weak acid and a strong base. And so what's going to happen there, and so here's an example. We have acetic acid plus sodium hydroxide. And so make sure that you understand where this is coming from. We're going to come up with our sodium acetate and water. So water is going to be in its liquid form. Now, as we're going through and we come up with our ionic equation, this is molecular. This is a weak acid. This is not going to completely dissociate. And so in our ionic equation, we leave it written in its molecular form because it's a weak acid, right? It's not going to split up into its ions. And so that's the way that we write it. So we leave it in its ionic form, meaning the only spectator ion here is our sodium. That's it. And so our net ionic equation is going to keep acetic acid in its molecular form plus our OH minus, giving us our acetate ion and water as a liquid. And so that's going to be your difference in coming up with a net ionic equation if you're working with a weak acid and a strong base. Non-metal oxides can also form acids in aqueous solutions. This is just another aspect of acid-base chemistry. And so, for example, carbon dioxide, so here's a non-metal oxide, plus water gives us H2CO3, gives us carbonic acid. SO3, sulfur trioxide, there's a non-metal oxide, plus water gives us sulfuric acid. These are important to note just environmentally because both of these are gases that are given off by the burning of fossil fuels. And so they can then react with water in the environment to form acids. You've probably at least heard the term acid rain. It's a big part of where it comes from. Now, fossil fuels certainly are not the only source of these. Volcanoes also give off some non-metal oxides like this. But so anytime that a non-metal oxide can get into the environment and get into the atmosphere, we can form acids and have the potential for acid rain. Metal oxides form bases in aqueous solutions. And so if we have calcium oxide, for instance, and add that to water, we're going to form some calcium hydroxide. So that's one way that bases can form. So the next driving force that we had mentioned earlier on, the next thing that might be able to drive a chemical reaction to happen is the formation of a gas. And so there are several gas-forming reactions that we're going to look at. And so, for instance, a metal carbonate or a hydrogen carbonate plus an acid give us a metal salt and carbon dioxide gas and water. And we can see that here. For instance, sodium carbonate plus hydrochloric acid give us our metal salt, our sodium chloride. CO2 gas is given off, and water. And then a couple others. So metal sulfide plus an acid also give us a metal salt and hydrogen sulfide gas. Metal sulfite and an acid give us sulfur dioxide gas and our metal salt and water, and then an ammonium salt. So let's take a look at why this happens. And so metal carbonate salts will react in sort of a typical exchange reaction. So here we have our HCl plus calcium carbonate. And so just like in any other exchange reaction, our positive ion, our calcium, is going to come together with our negative ion in the other reactant, the chloride, form CaCl2. Then our other combination, though, our H plus coming together with our CO3 to form H2CO3. These carbonates like this, and hydrogen carbonate in general, carbonic acid, pretty much immediately decomposes to form H2O and carbon dioxide. And so we just leave that intermediate step out when we're looking at the overall reaction, but that's happening in the middle here, is that first carbonic acid also forms and then splits apart and decomposes to form our carbon dioxide and our water. And the same thing will happen in this example with with hydrochloric acid and sodium bicarbonate. Will form salt and water and CO2. And so it's because of this. So again, it's because of this hydrogen carbonate, this carbonic acid, immediately decomposes and forms a gas. Another type of gas-forming reaction is that any group 1 metals, sodium, potassium, cesium, lithium, take any group 1 metal and put it into water, it's going to react very vigorously with the water and form the metal hydroxide, but it'll also form H plus gas, H2 gas. Those of you who were fortunate enough in high school to have sort of the classic sodium tossed into water demonstration, this is what was going on. Sodium gets tossed into water, and this reaction is quite vigorous, quite violent. And all the bubbling that you see is hydrogen gas. Hydrogen gas is flammable, so sometimes it actually catches on fire because the reaction has enough energy to give off some energy and occasionally some sparks. And so the hydrogen gas can catch on fire, and sometimes even just little explosion, kind of blows up a little bit. But it's because this hydrogen gas is forming. There are some metals that also react vigorously with acid to form hydrogen gas. So these are some other things that can drive a reaction to occur, is this gas formation. And another just example that we see sort of in everyday life, those of you who take Alka-Seltzer to settle your tummy maybe from time to time, what you're doing there, or what's going on there, is this neutralization reaction. Or what's causing the bubbles to form is that formation of the carbonic acid, then releases the hydrogen gas. Go on from there. Okay, I'm not going to worry about those. Sorry, we're going to move forward to our last topic for today, which is now looking at sort of this other driving force is an oxidation reduction reaction, where one of the things that can occur is the charges, and what we refer to as the oxidation number, can change. We can have electrons transferring to different places. So a good example of that is our thermite reaction, very violent, very, very exciting reaction that occurs that we can watch. Let's look at some details behind that. So what's actually happening in an oxidation reduction reaction, or a redox reaction, is that electrons get transferred between different reactants. Oxidation is the loss of electrons. Reduction is the gain of electrons. There's a couple different ways to remember that. My personal favorite is Leo the lion goes grrr. I know, it's silly, but I learned it that way probably 20 years ago, and it stuck in my head. And I still literally say that in my head sometimes when I'm working this type of problem. Loss or lose electrons, oxidation. Leo goes grrr, gain electrons, reduced. That's one way to remember it. Leo goes grrr. Lose electrons, oxidation. Gain electrons, reduction. Another one, if it works better for you, oil rig. Oxidation is loss. Wow, I cannot write today. Sorry. That's better, sort of. Reduction is gain. Again, just some little acronyms, some little ways to help us remember some of these terms. Oh, I guess I did have it right there. Oil rig. So let's look at an example here. So here we have calcium metal reacting with acid, and it's going to form our ion plus our gas. Calcium has no net charge to begin with. There's no charge on our calcium element. So it undergoes oxidation. It is oxidized to form Ca2+. It loses electrons, right? We're going from no charge, we're going from electrically neutral to +2. And so it is losing electrons to become positively charged. If something is oxidized, something else has to be reduced. And so the hydrogen ion, the H+, is being reduced because H2, now this is electrically neutral. And so we're going from positive to 0. Therefore, it had to have gained electrons. It had to have gained negative charges. Leo goes grrr. Gain electrons reduced. So the hydrogen ion had to be reduced there. When one reactant loses electrons, another reactant must gain them. The oxidation of one substance in a reaction is always accompanied by the reduction of another. These electrons are transferred between the two. And so to determine oxidation number, there are several different rules to go by. The oxidation number of an atom in its elemental state is 0. So something like the calcium metal that we saw just a second ago, that's an element in its, or an atom in its elemental state. Oxidation number is 0. H2 gas, oxidation number is 0. That is hydrogen in its elemental state. For a monatomic ion, something like Ca2+, the oxidation number is equal to the charge on the ion. Oxidation numbers for very common nonmetals are usually assigned in these ways. Hydrogen is a +1 when combined with nonmetals, a -1 when combined with metals. Oxygen is a -2 in most compounds, but it's a -1 in peroxides, and oxygen can actually have positive oxidation numbers if combined with fluorine in certain compounds. Halogens, fluorine is always a -1. Other halogens are a -1 except when they're combined with oxygen. In those cases, halogens can have varying values, which will be positive. And the algebraic sum for the oxidation numbers in an atom in a neutral compound is 0. In a polyatomic ion, the sum of the oxidation numbers will be equal to the charge. Back up. And so these are the rules that you want to use when you're trying to determine the oxidation numbers of elements within a compound. Go back to these rules and just go through these rules very systematically when you're trying to determine oxidation number. It is important to note that oxidation number and charge are not the same thing. We've talked about charge, as in the charge on an ion, and how we use that to determine a chemical formula. Charge is a real thing that exists due to an imbalance in an atom between the number of protons and numbers of electrons. And so if I have 10 protons, but only 9 electrons, then I have an extra +1 charge. And so that's a real physical amount. That's a real charge on that particular atom. Oxidation number, on the other hand, is more of just this sort of this artificial bookkeeping that we use to just track electron movement. It's a way for us to be able to note how electrons are being transferred in a redox reaction. And so in many cases, oxidation number is going to be equal to charge. Like in the cases of any monatomic ion, the oxidation number is equal to charge, but they are not the same thing. And we do write them differently. Charge, and we talked about this when we looked at ions a couple weeks ago. Charge is written with the number followed by the sign, and so a 1+, whereas oxidation number is written with the sign followed by the number. So that is an important difference in terminology. I know that I quite often slip up. You'll see me even on some of the examples that I gave today when I might have written charge as a +1. Really should be 1+ whenever you're talking charge, and +1 whenever you're talking oxidation number, because there is a difference between those two things. So let's look at some examples here. We want to find the oxidation number of sulfur in the following compounds. And so we're going to use the rules that were on our previous page. And so in H2S, we said that for hydrogen, when hydrogen is with a nonmetal, the oxidation number on hydrogen is going to be +1. We also said that in a neutral compound, the sum of oxidation numbers has to be 0. And so in this case, we can see that the oxidation number on sulfur has to be -2, because that's the only way to get our sum equal to 0. For sulfur dichloride, SCl2, halogens, we said, typically have a charge of -1, except when they're with oxygen. The chloride is not with oxygen, so it's going to have a charge of an oxidation number of -1. And there are 2 of them. That means that our oxidation number on sulfur has to be a +2. Go through those same rules, use the rules, and determine the oxidation number on sulfur for these last 2, for sodium sulfite and for sulfur tetraoxide. So take a minute, use those rules, determine the oxidation numbers, pause the video, go back in the slides. If you have to rewind in the video, go back to the rules and find the oxidation number on sulfur for the last 2. See what you come up with. Hopefully you got +4 for the last one, and for sodium sulfite, and +8 for the last one. And so this is again where we have to note that there's a huge difference between what charge is and what oxidation number is. If we were to ask what the charge on sulfur is going to be, then yeah, we use our periodic table on this side. And when sulfur forms an ion, it's in this column, so it's going to tend to form a -2 charge. That is very different from the oxidation number. Depending on the compound that sulfur is found in, the oxidation number can be all over the place. And that's again because oxidation number is just sort of this artificial bookkeeping method we have to track where electrons are moving and being transferred around in a chemical reaction or in a redox reaction. And so here's another way to visualize this. So here's a redox reaction between silver and copper. So we just have some aqueous silver with a 1+ charge, copper metal. And so in this case, the oxidation number on copper is 0 because it's in its elemental state. Oxidation number on silver is +1 because it's a monatomic ion with a 1+ charge. And so as we go from reactants to products, we can see that copper is donating electrons, right? Because copper is going from 0 to +2. So copper has to be losing electrons. So if copper's losing electrons, that means copper is losing electrons. So remember, every time in my head, I have to go through it too. Leo, loss is, and so I'll go through it in my head. And so since copper is losing its electrons, going from 0 to +2, then that means copper is being oxidized. Likewise, that means that silver has to be being reduced. And we can see that here. Silver's going from its +1 oxidation number to 0. And so that means that silver's going from its +1 to its 0. And so silver is gaining electrons, so silver is being reduced. Now, another way to think about this is that since so copper is being oxidized, that means that silver is causing copper to be oxidized. Therefore, silver is the oxidizing agent. Silver is making the other species become oxidized. And likewise, copper is making the other species become reduced. So copper is the reducing agent. And so the species in a reaction that is oxidized is also the reducing agent, and vice versa. The species being reduced is the oxidizing agent. So there's some other terminology that we have to keep in mind. And so this has been a fairly long presentation, but we've gone through several different types of chemical reactions. We've looked at precipitation reactions, where we're going to use our solubility chart and be on the lookout for a solid that's produced. We've looked at acid-base reactions, where the driving force is going to be that formation of water, the formation of a weak electrolyte. And we can identify those by identifying that we have acids and bases involved in the reaction. We looked at the formation of gases being one of our driving forces of a reaction. So we're going to look for gaseous products. The key ones we want to key in on especially are carbonates and sulfides reacting with acid to form our carbon dioxide gas or our sulfur dioxide gases. And then we also looked at oxidation reduction reactions. And to identify if something is an oxidation reduction reaction, we need to identify changes in oxidation numbers. We need to literally look through and find the oxidation number on every species in the reaction, see if any of them changed. If some of them changed, then it's an oxidation reduction reaction. There are a couple other types or a couple other ways to look at reactions. We have combustion reactions. That's any reaction where we have something reacting with reacting with oxygen. They produce heat and light. For instance, when a hydrocarbon combusts, it will also always produce carbon dioxide or carbon monoxide and water. We have a combination reaction, A plus B going to AB. A decomposition reaction, AB splitting up. Or exchange reactions, which we did look at, where ions are changing partners. Now, most of the types of reactions, most of these different types, can also be classified in the ways that we've already talked about. These are just other ways to think about some of these reactions that we've looked at. So like I mentioned, we have our combustion reactions. So something like methane, natural gas, reacts with oxygen in order to produce carbon dioxide and water. And that's really the big hallmark of a combustion reaction. O2 as a reactant. Fire needs oxygen. And we produce carbon dioxide and water. Combination reactions, two or more substances combining to form one product. Substances could either be elements or compounds. Decomposition reactions, where a substance decomposes into more simple substances. So we have water, for instance, decomposing into hydrogen and oxygen. Hydrogen peroxide decomposes into water and oxygen. Or we have exchange reactions. Several that we've already looked at are exchange reactions. And so precipitation reactions, for example, are just an exchange reaction. And that is everything for today. Lots of stuff here. We've covered lots of different aspects of chemical equations and chemical reactions in today's lecture. And so definitely make sure that you're going back and looking things over again, reading back through your notes, reading back through the textbook, seeing what makes sense now that maybe didn't before. Next time, where we're going from here is we're going to start to look at the amounts of things in chemical reactions, and we're going to get pretty math heavy starting with the next lecture. And so, as always, if you have any questions, be sure to send me an email, ask me anything that you're unclear on, and don't forget that we have tutors available at the Learning Commons. Some of you have been taking advantage of those tutors, and I encourage you to keep that up. As always, let me know if you're having any problems.